All right, so we're going to pick it up where we left off yesterday when we saw a large number of examples of how limits are calculated. So we did mention yesterday that there are two-sided limits and there are also what we call one-sided limits. So let's just take a look at a graph. All right, so here's where x equals 0. This is the function y equals x squared. And I may be interested in finding out the limit as x approaches 0 of this function. Now, this is our two-sided limit. And we solve this simply by plugging in 0. And we end up with, of course, 0. It's two-sided because it's the same value, whether we are approaching 0 from greater values than 0 or from left. Now, one-side limits means we're only looking at one side or the other. So, for example, here, if I'm approaching 0 from the positive numbers, then we can write this as the limit as x approaches 0 with a little plus sign. And then down here, if I'm coming from the smaller values, the negative values, I can write this as the limit as x approaches 0 from the left or from the negative numbers of the same function. So these two are both known as one-sided limits because they're only focusing on one direction. In other words, either we're approaching the constant 0 from the right or from the left. Now, I may think we mentioned yesterday too that the two-sided limit only exists if these two equal each other. Okay, now, of course, they both equal 0, which means that the two-sided limit also equals 0. But if they're different from each other, then the two-sided limit does not exist. Right. So in other words, one of the conditions for limit to exist is that the left and the right-hand sided limits have to equal each other. Now, for this particular example we're looking at, well, it's pretty clear that we can't have any values of x less than 3. We can have 3 itself, but not anything smaller than that. So the domain is everything from 3 up to infinity, including the 3. And here's why. This is what the graph looks like. More or less. It's not perfect, but it's a pretty good approximation to what this graph actually looks like. All right. So in other words, starting at 3, every value of x produces a value of y. Once we get below 3, we'll have a negative square root, which means we'd have an imaginary number. So what that means then is that if we're trying to take a limit as x approaches negative 3, which is way out here, well, the function is not defined in that area. So therefore, this limit is undefined. Now, in the next slide, we'll see, though, that in this case, we're interested in 3. Now, I see here that there's a typo here. I mean, this is not, I suppose you could say that it's not wrong, but it normally is written like this. I just noticed that. So I'll fix that later on. But normally the sign comes after the constant to indicate this isn't supposed to be a positive number, although it is. That means we're approaching from the right. So that would be our limit as x approaches 3 from the right of radical x minus 3. Now, here, all you would have to do is plug this in, and you'd end up with 0. Now, here's an interesting one. We have what's called a piecewise function, which means its behavior is very different over different intervals of the real number line. So this one, for example, you can see that when x is below 2, then this function is a straight line. it's going to reach approach, but not quite reach 2. So I'll indicate that with a hole. And then all of a sudden, it becomes a parabola. So the left-handed limit here, or the limit from the left side, is equal to 4 times 2 minus 3, which is 5. From the right-hand side, we have 1. Okay, so actually I haven't drawn this right. Let me try that again. Actually, I'll tell you, let's just throw it into Symbolab. Now, I've had this issue with Symbolab before. I know technically it's capable of doing this, but I have to probably read the instructions or go to Google. All right, here we go. What do we have here? So, oh, here we go. It is set up. Okay, you can see what they've done. So I have to copy this. 4x minus 3 is one piece of the function. And that's valid as long as x is strictly less than 2. And once we get to 2 itself, we have x minus 3 squared. And this, of course, implies or applies from 2 and up to infinity. All right, let's see what this thing looks like. Yeah, so look how weird that is. So yeah, I started to draw it incorrectly. The straight line segment, this is the 4x minus 3. It's a straight line, fine. It cuts through the axis at -3, as you can see. And then when we just about reach x equals 2, there's a hole. Okay, the function, this portion of the function, or this piece of the function, is not defined for any numbers from 2 and up. So that's indicated by a hole. And then here, this function, this is a parabola, obviously, starting at 2, where the value of y is 1. The curve continues. Now, the important detail here is that the limit coming from the left is 5. The limit coming from the right is 1. So it has 2 one-sided limits, but they're not equal to each other. So that means there is no two-sided limit when x equals 2. They have to be equal to each other. So yeah, in the next slide, it shows you the calculations from the left-hand side. 2 negative is what that indicates. We're coming from the left, and that piece has a value, or it approaches 5 as x approaches 2 from the left. As we approach from the right, the function changes to x minus 3 squared. So as I get very, very close to 2, I'm going to wind up with 1. So therefore, the 2 are not equal to each other. And therefore, the two-sided limit does not exist. Or you could also say it's undefined. All right. Now we've got some theoretical results that we want to just take a quick look at. We don't need to spend too much time on this. We have theorems that help us determine what the behavior of functions will be under certain circumstances. We have the squeeze theorem, where you're basically saying, listen, suppose you've got these two functions, f of x and h of x, and they have the same limit when x equals a. That's the key to the whole thing. So what they're basically saying is that if we can prove that g of x is always in between the two, that implies let me just write this in. The limit is x approaches a of h of x, the one on top, is, we'll just call it, I don't know, f of a. Or actually, they're calling it capital L, so let's stick with that notation. The limit of the bottom function, f of x, as x approaches a, is also capital L. It's just some constant. So if you can prove that no matter what, g of x is bounded between f of x and h of x, actually, this doesn't have to be for all real numbers, by the way. I just want to mention that this is actually, it's okay if this is only for an interval containing a. After that, it hardly matters, because we're only interested in the limit as we approach a. So we only need them, although in this graph that they've shown us, they are indeed, g of x is in between the two. If you notice, we don't know for sure. We don't know that g of x, for example, doesn't just suddenly go up like that. And that's okay, because within some range here, you can see that the behavior we need is correct. G of x is always in between the other two. And what that implies is that we don't even have to calculate the limit of g of x. It's going to be the same. So, what the reason why this might come in handy is because you might have a function g of x whose limit you're trying to calculate, and it may be a very messy function, but you might be able to find two other functions that surround it that are much simpler. It might be easier to evaluate their limits than directly calculate g's limit. All right, so now here's an interesting example. Evaluate the limit of x times the cosine of x. Well, it turns out that the cosine of 0 is 1. So that's going to leave us with 0. Now, if you look at this graph, you've got three functions, absolute x, and these are the two outside functions. Negative absolute value of x, positive absolute value of x, cosine of x. You can see by the way the graph is drawn that at least over this interval, g of x is in between the other two. Okay, so I guess they shouldn't have done it this way. This is what we meant by f of x. This one is h of x. Okay, so remember, the point of this is that g of x is bounded between the other two, at least within that interval. So here's the point of interest, 0. So what they're essentially saying here is that all three limits have to be the same. By the way, they're going to try to prove it here by mentioning that if you look at the graph of the cosine of x, which we can do in Symbol Lab, If you look at it carefully, you'll see that it's really going through a series of these waves. And if you notice, it never goes above 1 or below -1. So the range of this function is between -1 and +1, which is equivalent to saying that this function will never go outside the range negative to +1. So that now, of course, you know that the absolute value functions are not bounded within that range. They can definitely go outside that range. So the two limits here, you can see, are both going to give us 0. So this implies that the limit of g of x is going to be 0. Now, if you wanted to do this directly, there are ways we could do it. We don't need the squeeze theorem, but this is going to be a very messy case, and it's something that we'll have to save for later. But for right now, it's enough to note that we can reason out that this has to be 0 because of the way it's bounded between the two other functions whose limits at x equals 0 are themselves 0. Okay, so we're not going to really use this for anything else. We just want to know that this theorem exists. A lot of these theorems could potentially be helpful, but we don't necessarily need to use them. They're not required, is what I'm saying. Now, in a more advanced class, you might be asked to demonstrate why these theorems hold. But for now, we're just going to go through and see what their consequences are. Now, here's an important concept in calculus, the notion of continuity. In a nutshell, a function is continuous. And this is a very informal way of explaining it. If I can draw this graph without ever taking my pencil off the paper, then it is continuous. And it's really that simple. In other words, I can draw a line without ever stopping, and it is therefore continuous. Now, something like this is clearly discontinuous. At x equals, let's say, a. At point A, the function's behavior is different coming from the left and coming from the right. So this is one of those piecewise functions. So this function is said to be discontinuous. Now, sometimes the function can have different kinds of discontinuities. Here, it's only taking place at a single point. And so that may not be a problem for whatever we're trying to do. So like, here's an example. Here's a function that is discontinuous at that one point. F of a is undefined. Okay, in other words, when x equals a, the function is undefined. And that's what we mean by discontinuous. And it doesn't have to be split like that. In other words, this one has two separate pieces. It's also discontinuous. Now, as we saw earlier, this one has two different limits, one from the left, one from the right. They're not equal to each other. And therefore, the two-sided limit does not exist when x equals a. And that implies that the function is discontinuous. Okay, so in other words, the fact that the limit does not exist tells us that the function is discontinuous there. So in general, we have the limit from the left and the right are different, the limit is undefined, as we know, which implies the function is discontinuous. And you can have something like this too. You have the function is not continuous because this time the problem is that here's f of a. This is our limit. Now, if you notice, this limit does exist. Let's call this L. But so the two-sided limit does exist. But guess what? It's not equal to f of a. And that also is enough to indicate that the function is not continuous. All right, so in other words, you can see we've seen two ways in which the function can be discontinuous. So this list is telling us that in order for a function to be continuous, three things have to be true. So in other words, f of x is defined at x equals, oh, what did I do? This should have said x equals a. It's defined at that point. In other words, it's just a hole. The limit exists, as you can see. It does here because the two limits are equal to each other. The limit from the left and the right, and they're both equal to L. Let's call it L. Okay, so we know this is true. We know that f of x is defined at x equals a. And then the limit, which we're calling L, equals f of a. So all three conditions have been met. So in other words, in order for it to be continuous, there must be, it must actually have a value at x equals a. It must have a two-sided limit, and the limit must equal f of a. So you can see why, like down up here, we had this one. The problem here is not one, not two, but number three is wrong. Okay, so in other words, with this case, the holdup is number three is not correct. And therefore it is not continuous. With this graph, the problem is that numbers 2 and 3 fail to hold. Okay. So all three have to hold in order for the function to be continuous. All right, now, polynomials are continuous for all real numbers. Rational functions are continuous for all values of x except when the denominator is 0. Remember, a rational function is simply one that is a ratio of two other functions, something like this. And remember, a polynomial from chapter 1. It's basically a stream of x to some power with a coefficient where the ends are all rational. So it turns out both of these are guaranteed to be continuous unless in the first case we have division by 0. So here's the polynomial f of x equals x squared. Very simple case. So let's say a is here. This will be f of a equals a squared. And then the limit is a squared. So L equals f of a. And then the limit exists, and the function is defined at this point. So there's the function is defined, the limit exists, and equals f of a. So therefore, this is a continuous function. Now here, oh, by the way, here's the graph for x plus 1 over x minus 5. So you can see it's going to be continuous except at the asymptote x equals 5, because f of a is not defined. The limit does not exist. Man, this one fails in all three ways. And the limit wow, this one is a 3-time loser, isn't it? Yeah. In other words, this one does not satisfy any of the 3 requirements for continuity. Now, it turns out, as you probably get a sense of this by looking at the graphs we had before, there's 3 basic types of discontinuities. Now, it matters a great deal which one our function has. If there's a discontinuity, it matters a great deal if it falls into one of these 3 categories. Because sometimes, even if the function doesn't satisfy our requirements, there may be ways of working around that. It depends on which one is the problem. Which type of discontinuity do we have? So we have removable, jump, and infinite. So removable means that we just have a hole. Like we've seen this one before. This is a removable discontinuity. Okay. So there's a gap here. Actually, you know what I'm going to do here? Let me go and get the 3 requirements back. Just so that we can refresh our memories as we go along. All right, here we go. These are the 3 requirements for continuity. Oh, I know what I need to do. I have this wonderful software product that Snagit. If I had a Mac, I mean, I'd be, it has its own built-in function, but this is does a good job. I can copy whatever I need. All right, so what's the problem here? F of x is actually this one, f of a rather. So the first one is okay. The limit exists because you can see that the limit as x approaches from the left, we'll call this L, equals the limit as we approach from the right, and we're going to call that value L. Here's what the problem is. Right there. L, as you can see from the graph, does not equal f of a. So therefore, this function is not continuous at that point. Now you can see it's continuous everywhere else, but it's not continuous there. So we need this information. Well, and that's the reason. It's number 3. That's the holdup. Now, jump discontinuity. We saw this one earlier, where we actually have the two pieces. It's a piecewise function. It's not the case that there's a hole, just a hole. We actually have two distinct line segments. So this implies, now f of x does exist at a. So condition 1 is met, but you can see the limit from the left, whatever that is different from the limit coming from the right. So that means that the two-sided limit does not exist. So number 2 is out. And then, of course, number 3 can't exist if the limit itself doesn't exist. Okay, so the third one can't be true if number 2 is false. Now, infinite discontinuity, this is the one where we have an asymptote. Oops. All right, let me get a copy of that graph again. Not graph, chart. Here we go. All right, I need to copy this again. So the first one already fails. F of x is not defined. Well, that lets that out. And of course, you can see that coming from the left and the right, the two limits would be different from each other. One is, by the way, positive infinity, and the other is negative infinity. Uh, the, the tablet is having a rough time tonight. Every once in a while, the tablet just stops working and it gets tired, I guess. So the first two are false. I mean, and we, of course, don't have to worry about the third one, but if the limit doesn't exist, then clearly it cannot equal f of a. So this fails in all 3 counts. All right. So here's a function. Let me show it to you on the next slide. What type of discontinuity does it represent when x equals 2? All right, now remember, this is the one that we called earlier the so-called removable. Now, why do we call it that, by the way? Well, here's why. Because what you could do is something like this. Suppose you have this function. And, it says here that it's x squared minus 4 over x minus 2. You could turn it into a piecewise function. Just say, well, it's x squared minus 4 over x minus 2 everywhere except where x equals 2. And then you could basically provide this value. And lo and behold, you have yourself a continuous function. So, in other words, it says removable. You can have a discontinuity that can be fixed. Now, how about this one? Now, this is very similar to one we had earlier. And what you can see on the next graph is that when x equals 3, you can see that there's an actual gap in the two segments of this function. Okay. Okay, so this is the so-called jump discontinuity. Jump meaning there's a gap. It's like you're jumping from one level to the next when you reach this point, x equals 3. And so even though there's a left and a right-handed limit, they're not equal to each other. And that's why they're discontinuous. Okay. So in other words, this is 4. And down here, the limit, as we come from the left, is actually -5. And they're different from each other. So therefore, the two-sided limit does not exist. Okay. And, you can imagine that the third type, the infinite discontinuity, it would be easy to find examples of that. For example, just something as simple as y equals 1 over x. Has an infinite discontinuity when x equals 0. Okay. And that's again because the limit, as we come from the left, is negative infinity. And so they're not equal to each other. Very good. Continuity over an interval. Now, up to this point, we were focusing on a single point. What about intervals? Can we prove that a function is continuous over an entire interval, not just at a single point? And the answer is yes. So a function is continuous from the right if for some constant a, the limit is equal to f of a. Okay, in other words, is a. Let's just say that we decide to take the limit as x goes to b. Whether we approach from the left or the right, it's going to be f. In this case, it's f of b. Actually, instead of writing it L, because that would imply that it's a constant, we'll write it as f of b. And then same thing for c. The limit as x approaches c is actually f of c. Now, when we get to after a, I mean, the function can go crazy and do anything, but as long as it's from a up to infinity, we say that the function is continuous from the right, which means the entire function from a up to infinity. And of course, we can say the same thing about continuity from the left. All right, so here's an example of this. Now, it's pretty clear that there's going to be some asymptotes in this graph. You've got a quadratic function in the denominator, which means there's two x's that will lead to division by 0. Now look at this thing. Oh my God. So why don't we figure out the domain of this function, which is not always easy to do. All right, let's see what we can do here. The function is x minus 1 over x squared plus 2x. All right, so what we're trying to do is to find the domain, we're looking for points where we have division by 0. Okay, so in other words, okay, so what this implies is that the domain of x, the domain of the function, I should say, is every real number except 0 and -2. So using this notation, this is how we can write it. Okay, in other words, we just have to avoid a 0 and -2. Okay, and so it's not that clear. Well, they could have done a little better job labeling this, but those are the two asymptotes. And so what that means is that the function is continuous in the three intervals, but not at those 2 points. Okay, so it's continuous everywhere except when x equals 0 and when x equals -2. All right, now we've got a couple more theorems to look at. The composite function theorem. Now, just a quick review what a composite function is. That type of thing. Okay, so it's a function which is a function of another function. So this theorem basically is saying that if f of x is continuous at L and g of x has a limit as x approaches a, Um, okay. Then the limit of the composite function is f of L. All right, so let's look at an example of this. That's a very abstract idea. F of x is continuous at L. And the limit, these are the two requirements. The x goes to a, g of x equals L. This implies that the limit of f of g of x is f of L. All right, so let's see what this is all about. First, oh, by the way, I just want to show you again how to calculate a composite function. We're told here f of x is x plus 1. G of x is x squared minus 7. F of g of x. Actually, we could write this like this if you want to. Just a reminder that all you're doing was replacing all the x's here with g of x. So you're going to have x squared minus 7 plus 1. Okay, now, what if we need to know the limit as x goes to 3? Of g of x. Okay, so there's this, you notice how we've got limit g of x as x goes to a is L. So what it's telling us is that the limit as x goes to 3 of f of g of x is f of 2. So let's prove it. All right, so remember before we saw that f of g of x is x squared minus 6. Now f was originally x plus 1. So therefore, the limit of this function, composite function, that would be since f of x is Lx plus 1, which is 3. All right. And then finally, the intermediate value theorem. Basically, all it's saying is that if f is continuous over an interval, let me show you this graph. F a to b is some interval where the function is continuous, and f you can see the corresponding f of a and f of b. Z is somewhere in between f of a and f of b. What this guarantees is that corresponding to the z is some c, which is in between a and b. In other words, z being between these two implies that c is somewhere between a and b. So we're not going to use it for anything particular right now, but we're going to get back to this. We're going to need this. You'll see down the road, we'll be able to use it to justify some more advanced results. But right now, it's just important that you are familiar with this idea. So now it looks to me like we're ready to take a peek at chapter 3. Now, I did mention this once before. This is easily one of the most important chapters in the book by a long shot. Derivatives. A large percentage of what we do in calculus is taking derivatives. So what we need to do is figure out what exactly is a derivative, and then we're going to be introducing many, many rules that will help us calculate complex derivatives. Okay. So we're going to be looking at what a derivative is in the first place. We're going to introduce some rules, and then we're going to differentiate at higher levels. In other words, with higher order differentiation, what you're effectively doing is taking the derivative multiple times. Now, here's the secant lines. Remember, a secant line means you've got some function and the secant line crosses through it twice. That's a secant line. Okay. Now, the slope of that secant line could be defined in the following way. Actually, let me show you the graph, and then we'll do it. The definition is down here at the bottom. So you have 2 points, a f of a, x f of x. So the slope, which is, of course, delta y over delta x, is f of x minus f of a over x minus a. Now, if you can imagine, now they're going to change the notation here a little bit. You'll see why in a second. We're going to have a and a plus h. H is some small amount which we've added to a. So what we're basically going to do is imagine what happens is these points get progressively closer to each other. In other words, what we want to know is what happens as h, the difference between the 2 points, approaches 0. And so what's going to happen is the lines will get closer and closer. I mean, the points rather. And so eventually you'll find that the line is touching the curve at exactly 1 point. And at that point, what you have is a tangent line. Okay, in other words, instead of a secant, it is now a tangent. And so here there, this is so hard to draw properly, but you can see eventually we end up with a tangent. And here's the most important thing. The slope of this tangent line has a special name in calculus. This is called the derivative of f of x. Okay, so the word derivative means the slope of a tangent line to the function at that point. All right. So formally, we can write it as there's two definitions that are equivalent to each other. As x goes to a, or in the next slide, you can see that this is equivalent to saying remember we had two different graphs. When we had a and x as our 2 points, it looked like this. When we changed it to a and a plus h, it looked like this. They both mean the same thing. So all we're doing here is calculating the limit in two different ways. Any way you look at it, in either case, you're going to wind up with your tangent, the slope of your tangent, and those are both known as the derivative of f of x. Okay. Now here's a good one. Now here, what we're going to do here is we're going to actually calculate the derivative using this definition. The function we're interested in is f of x equals x squared. At the point x equals 3. It's equal to the slope at that point. So how do we figure this out? We're going to use this definition. And so the a is 3. So we get f of x minus f of 3 over x minus 3. Now f of x is itself x squared. And therefore f of 3 is 9. So in the numerator, we have x squared minus 9. In the denominator, it's just simply x minus a. We're going to take the limit as x approaches 3 of this expression. Now, we have to watch it here because if you directly substitute, you're going to wind up with a 0 over 0. So here's what we have to do. And we saw these the other day. If you've got two functions, you can show that the two of them will have the same limits. So that if you have one where there's 0 over 0, you can replace it with a different function. Here, for example, we can replace this function with this one. So you actually end up with 6. Now, here in this graph, you're going to see what this is all about. So in other words, at that point, x equals 3, the tangent line is this blue line, and this is its equation. And clearly it has a slope of 6. And that means that the derivative of f of x at x equals 3 is 6. Or you could think of it this way. At precisely that point, if I increase x by 1, y will increase by 6. Now, this is only true if you increase x by an infinitesimally small amount, but that's how we can interpret it. All right. So I don't want to get too far ahead here. There's several more theoretical results to look at here, and then we can start doing some actual formulas. Yeah. Oh, we've got a ways to go here. And then once we get to the formulas, it'll start to become a lot more straightforward. Nobody require, I mean, you're never going to be told you must calculate derivatives with limits. At least it's not likely. Maybe once, or maybe with a simple example. For the most part, we'll be using rules. Okay, but it's awfully important to be aware of where these derivatives are coming from, what they actually mean. All right, so we'll pick it up next time with our discussion about derivatives. And so I'll see you then.